Welcome to AI Paper Podcasts. We're the place where we, cut through the jargon and really try to get to the core insights of the latest AI and tech research. Basically making it useful for engineers and researchers like you. Today, we're diving into a really fascinating paper. It's titled TamedPUMA, Safe and Stable Imitation Learning with Geometric Fabrics. And our mission for this deep dive is to unpack how this new algorithm tackles a really critical and often frustrating challenge in robotics.
Right. Teaching robots complex tasks, especially when they need to be safe and reliable around people or in messy, unstructured places, that's tough.
Exactly. Imagine trying to teach a robot something delicate like pouring water or picking fruit just by showing it once and wanting it to just do it flawlessly without bumping into anything, without, breaking itself, even if things move around unexpectedly, like the glass moves or your hand gets in the way.
Yeah, that's the kind of robust, intuitive interaction TamedPUMA is aiming for. It's a big goal.
So, okay, let's do the quick 1-minute summary. What's the absolute core of TamedPUMA? We know imitation learning, IL. It's great for copying motions, right?
Right. It captures that human-like movement. But, and this is the big but, it really struggles with safety in the real world. Physical constraints, collision avoidance, not its strong suit.
So TamedPUMA steps in. It's described as a breakthrough solution. How?
Well, it cleverly combines that imitation learning with something called geometric fabrics, which is a framework specifically designed for motion generation that is inherently safe.
Okay, so the big idea is you take the motion learned from the human demo.
Yep, the task-specific policy from IL.
And you seamlessly blend it with these geometric fabrics.
Exactly, and the fabrics handle the collision avoidance, the joint limits, all that safety stuff automatically.
So the result is a robot that learns these stable, goal-reaching motions from a human,
while rigorously and in real time making sure it's safe and respects its own physical limits.
And they actually showed this works.
Oh yeah. The paper demonstrates it with a 7 degrees of freedom robot arm. They got a 100% success rate on tasks like picking a tomato, pouring liquid, even with dynamic obstacles moving around.
Wow, 100% is significant.
It is. And the computation time is incredibly fast, like 4 to 7 milliseconds. That makes it actually practical for real-world use, not just a lab curiosity.
Okay, so that's the snapshot, a real potential game changer for adaptable robotics.
Definitely. But okay, let's unpack this properly. To really get why TamedPUMA is important, we kind of need to look at why we need something like this now.
Right. What's the societal push?
And then we'll break down the components, the IL part, the fabrics part, and look at the two really clever ways they actually combine them.
And finish off with those compelling experiments, sim and real world.
Sounds like a plan.
So let's start with that big picture then. Why this need for something like TamedPUMA in robotics right now? What's driving it?
Well, the simple answer is robots aren't just in factories anymore, right? They're moving into our homes, onto farms, into hospitals. Think assistive robots, agricultural automation.
Places that are inherently unstructured and unpredictable.
Exactly. And that creates two huge demands. First, regular people, non-experts, need to be able to teach these robots new tasks easily. Programming them manually just doesn't scale, and it's way too expensive.
And second, and this is crucial,
they have to operate safely alongside us humans, and safely in environments that are constantly changing. That's non-negotiable.
And that's where, as you mentioned, traditional imitation learning kind of hits a wall. It sounds great on paper to learn by watching, but what are the real sticking points?
Precisely. IL is super intuitive. You demonstrate, the robot learns a motion profile, often encoded as a dynamical system so it reliably gets to the goal. That part's good, but it usually only cares about the task space motion, like where the robot's hand, the end effector, needs to go. It fundamentally struggles with the physical realities, the robot's arm bumping into the table or its own base, or exceeding its joint limits. These constraints are often an afterthought or handled poorly.
So despite tons of research, nobody had really cracked how to guarantee both things at once. That is, stability always reaching the goal and real-time handling of all physical constraints, especially for complex robots like a 7D arm.
That's pretty much the situation, yeah. It's a really hard problem. And that's the gap TamedPUMA is explicitly designed to fill.
Okay, so let's get into TamedPUMA's core innovation. It builds on IL and geometric fabrics. You said they create inherently stable and safe motion primitives.
Right, and the key insight, the thing that makes it possible to blend them, is that both IL policies and geometric fabrics, mathematically speaking, describe motion in a similar way. They both use artificial second-order dynamical systems.
That shared language is the bridge. And for folks maybe less familiar with dynamical systems in robotics, Think of it like defining the physics of the robot's desired movement, right? Like equations that guide it towards a stable state or goal, kind of like gravity pulling a ball downhill.
That's a good way to put it. And focusing on the geometric fabrics part first, you can think of them almost like adaptive force fields ensuring safety. They aren't just about getting to the goal, safety is baked in from the start.
How so?
Well, a fabric system has two main components. One part is energy conservative. It actively pushes the robot away from obstacles and joint limits. Think of it like a repulsive force field.
Okay, the safety shield.
Exactly. The other part is energy decreasing. This acts like a pull towards the target, ensuring the robot actually makes progress and converges to the goal. It's like a guiding force. So you have this unified system managing both safety and goal seeking simultaneously.
That makes sense. And it's clever how they handle multiple constraints, too. You mentioned defining them in different task spaces.
Yeah, you can set up rules for, say, the end effector avoiding a specific object, and separate rules for keeping the elbow joint within its limits. Then the framework pulls back all these individual rules into one cohesive policy for the entire robot in its full configuration space, so it considers everything together.
Got it. So that's the fabric side and in the safety and goal convergence.
Yeah.
What about the IL side? They use something called PUMA.
Right. PUMA stands for Policy via Neural Metric Learning. It's the specific IL method they build on. PUMA also models the desired motion, usually the end effectors, as a dynamical system. It uses a deep neural network, a DNN, trained on those human demos.
And the key here is stability.
Yes. PUMA is designed specifically to ensure the goal state is a globally asymptotically stable equilibrium. Basically, wherever the robot starts, it should always end up at the goal.
And they achieve this stability during training using a special loss function, OSTable.
Exactly. Alongside the normal loss that just tries to imitate the demonstration, they add this a stable loss. It uses ideas from deep metric learning to actively push the learned system towards being stable. It's not just copying, it's learning how to be stable while copying. It ensures the target point really acts like a stable bottom of the valley for the robot's dynamics.
Okay, so we have PUMA for learning stable, human-like motions and geometric fabrics for inherent safety and constraint handling. Now, the million-dollar question, how does TamedPUMA actually merge these two?
Right. The overall goal is to learn a system that follows the demonstrated trajectories. Well, they measure this using Kullback-Leibler divergence, basically minimizing the difference while strictly satisfying two big constraints.
Sure.
One, the robot must always converge to the goal, no getting stuck. Two, every part of the robot has to stay in free space, avoiding all collisions and joint limits. Always.
And PUMA handles the imitation convergence sort of softly, while fabrics handle the hard constraints. Merging them perfectly is the challenge.
It is. How do you blend PUMA's learned goal seeking with the fabric's bulletproof safety? TamedPUMA offers two ways to do this.
Let's hear them. Method one.
Method one is the forcing policy method, or FPM. This approach is conceptually quite direct. You take the learned PUMA policy, which usually just describes the end effector motion, and you pull it back mathematically to get corresponding desired movements for all the robot's joints.
So you translate the hand motion into instructions for the whole arm?
Precisely. Then this whole body PUMA policy is used as a forcing term within the geometric fabric system. It essentially tells the fabric system this is the direction PUMA wants to go.
Okay, so PUMA provides the guidance, and the fabric ensures safety along the way. Seems neat. Is there a catch? You hinted earlier.
There's a subtle theoretical one, yeah. Geometric fabrics are conservative systems. What that means is if the robot happens to reach a state where the PUMA policy's desired velocity is 0, like the goal, it will stay there. But FPM doesn't formally prove that the robot will always reach that PUMA goal from any starting point when combined with the fabric dynamics.
So it works great in practice, but the absolute mathematical proof of convergence isn't quite there.
Pretty much. It's a fine point, but for situations demanding absolute theoretical guarantees, they developed the second method.
Which is the compatible potential method, CPM. How does that one provide a stronger guarantee?
CPM uses a concept called a compatible potential function. You can think of this like creating an energy landscape for the robot, where the goal state is the lowest point, the single valley bottom.
Like the stable equilibrium idea again?
Exactly. It's a scalar function, just a single value for each robot configuration, and its negative gradient, the steepest downhill direction, always points the same way as the desired motion from PUMA.
Okay.
And the neat mathematical trick is, if you can find such a compatible potential function for your desired motion, you can then construct a new dynamical system that is guaranteed to converge to the goal, the potential minimum, while also incorporating the avoidance behaviors from the geometric fabric.
So how do they get this potential function?
They cleverly use the latent space of the PUMA neural network. Because PUMA is trained with that stable loss, the network inherently learns a representation that acts like a potential function, with the goal being the minimum. CPM leverages this structure.
Makes sense. Now, you also mentioned a small trade-off with CPM, something about avoidance at the goal.
Ah, yes, a nuanced detail from the paper. Due to an assumption they make about a specific metric, MLO, used in the CPM formulation, while collision avoidance is guaranteed along the path as the robot is moving towards the goal. It's not theoretically guaranteed in the limit, like precisely at the exact moment it reaches the goal state. It's a subtle point, likely negligible in practice, but it's a theoretical trade-off they acknowledge for getting that stronger convergence proof.
Interesting. Okay. Theory is one thing. How did TamedPUMA actually perform in practice? Let's talk experiments.
Right. This is where it gets really convincing. They tested both FPM and CPM extensively. The main platform was a 7 degrees of freedom QKIIWA manipulator arm.
Standard research robot.
And they tested in simulation and the real world. Both. They used PyBullet for simulation and then ran it on the physical KUK. They focused on 2 tasks that need dexterity: picking a tomato from a crate and pouring liquid from one cup to another.
Things that require careful movement.
Definitely. And get this, they trained the DNN for each task using just 10 human demonstrations. That's it. Just recording end effector position, velocity, acceleration.
Only 10. That's very data efficient.
Extremely. For collision avoidance, they modeled the robot's last 5 links as spheres a common simplification. And crucially, they introduced dynamic obstacles tracked in real time with an OptiTrack motion capture system. Things like a moving bowl, someone waving their hand near the robot, even a helmet.
So really testing the reactive avoidance, who did they compare against?
They benchmarked TamedPUMA, both FPM and CPM, against the baselines you'd expect, just using vanilla geometric fabrics, just using vanilla PUMA, and also a common alternative method called modulation IK, which tries to modify inverse kinematic solutions to satisfy constraints.
And the metrics: success rate, speed.
Yep. Success rate, collision-free motion to the goal, time to success. Computation time, really important for real-time use. And also path difference. How closely did it follow the original learned PUMA path while avoiding things?
Okay, let's hit the highlights from the simulation results. The success rate.
This is the headline number. Both TamedPUMA FPM and CPM achieved a 100% success rate in the simulations. Perfect score.
Wow. And the others?
Big difference. Vanilla PUMA alone only managed 40%, lots of collisions. Modulation IK got 57%. Vanilla fabrics did better at 83%, but the paper notes it often got stuck in deadlocks, failing to reach the goal even without colliding.
So 100% is a massive jump in reliability. What about following the learned path? Did adding the safety layer mess up the intended motion?
That's another impressive part. TamedPUMA kept a really small path difference compared to the original PUMA path, just 0.02 to 0.04 meters on average, so it stuck very closely to that human-like demonstrated motion while smoothly avoiding obstacles.
And fabrics alone deviated more.
Much more, about 0.22 meters deviation. So fabrics prioritize safety but didn't preserve the learned motion style nearly as well. TamedPUMA gets you both.
Okay, now the computation time. You said it was fast.
Incredibly fast, like 5.22 milliseconds for FPM, 6.55 milliseconds for CPM, running on a standard laptop. This is well within the limits for real-time control loops, which often run at 1 kilohertz or 1 millisecond per cycle.
And crucially, how did it scale with more obstacles? That often kills optimization methods.
Exactly. They tested adding up to 1,000 obstacles in the simulation. TamedPUMA's computation time barely increased. It was still in the millisecond range.
Whoa. And modulation IK.
That scaled terribly. With 1,000 obstacles, modulation IK took around 3.5 seconds per computation. Totally unusable for real-time reaction. The speed and scalability really sets TamedPUMA apart for dynamic environments.
And interestingly, FPM and CPM performed similarly well in these practical tests, despite the theoretical differences in guarantees.
Yeah, in practice, they were both very effective and very fast. CPM's stronger theory didn't seem to translate to a noticeable performance advantage in these specific tasks.
Okay, simulations are great, but the real test is the real world. Did it hold up on the actual KUKA arm?
It absolutely did. The real-world tests mirrored the simulation success. TamedPUMA managed the tomato picking and the liquid pouring tasks smoothly, dynamically avoiding real obstacles like a moving bowl or a person's hand entering the workspace.
And what about robustness? Like if you bump the robot or change the goal mid-task?
They tested that too. If they pushed the robot off its path or even updated the target goal location while it was moving, TamedPUMA recovered gracefully and converged to the new goal. That really demonstrates the stability aspect. It's not just blindly following a trajectory. It's a closed-loop, stable system that can handle disturbances.
That's essential for any robot working outside a cage, especially near humans.
Totally. It shows it's not brittle.
Okay, let's wrap this up. Thinking about the big picture again, what's the major takeaway here for robotics researchers and engineers?
Well, I think TamedPUMA really represents a significant step forward. By integrating IL and geometric fabrics in this smart way, leveraging their shared mathematical foundation, they've created something that lets robots learn complex, quite nuanced, human-like motions just from a few demos.
While also providing really strong, real-time guarantees on safety, whole-body collision avoidance, joint limits, the works, and ensuring it actually reaches the goal reliably.
Exactly. It tackles that core dilemma of wanting robots to be both intelligent learners and fundamentally safe.
And the performance numbers, that 100% success rate, the millisecond computation times, they show it's not just a theoretical construct. It's potentially very practical. It pushes us closer to robots that can actually learn and adapt safely in our world.
It really does. It opens up possibilities.
So let's leave our listeners with a thought. Given what we've discussed about TamedPUMA, this ability to blend intuitive learning with hard safety guarantees in real time, what new places could you see robots being used effectively? Environments that were maybe too complex, too dynamic, or just too dangerous before?
Yeah, think about that. How could this change how you might interact with the robots day to day? Moving beyond simple, pre-programmed stuff to robots that are genuinely adaptable, helpful, and crucially safe partners. Maybe in your home, maybe in specialized fields like intricate assembly or even assistive surgery. Where does this capability unlock the next wave of robotics?
Definitely something to ponder. It's exciting to see this kind of progress.